good. Right, let's go. So, we're talking about larger stars now. Larger stars. After the main sequence star, a larger star finishes its life cycle in the following evolutionary stages. So this time it's a red supergiant, then it's a supernova, then it's a neutron star or a black hole. Okay, so a very different trajectory. So what is the red supergiant? So after several million years, the hydrogen that fuels the fusion, okay, the hydrogen that fuels the fusion in the star will begin to run out. So I'll just say that one more time. After several million years, the hydrogen that fuels the fusion. Do you know what this? Sorry, I know this is a bit of a side point, but doesn't this just show you that everything has a beginning and an end? Everything in the reality of in the anything that's bound by space and time, anything that's bound by space and time has a beginning and end. Think about what I just said there. I'll let you think about dwell on that later. Yo, Chris, you know. Right, okay. So after several millions of years, the hydrogen that fuels the fusion reactions in the star will begin to run out. Okay? Will begin to run out. Guys, I think this science is just allegorical at this point. Right, so the hydrogen that fuels the fusion reactions start to run out. So it's starting to run out. It's going now. It's depleting. Once this happens, the fusion reaction in the core will start to die down. Right, I think we need to note this down, guys. There's some serious facts here that we need to note down. So, definitely get this part down. So we know that the fusion reactions in the star begin to run out, and once this happens, the core will start to die down. The star will begin to fuse helium to form carbon, so we're getting heavier elements, so quite similar to the red giant. This is followed by further fusion reactions in which nitrogen and oxygen are formed. So again, heavier elements. Heavier elements up to iron are formed. Okay. Right, are we good on this, yeah? So we're going from fusion reactions run out, the core starts to die down, helium to carbon, nitrogen to oxygen, all the way up to iron. So the heaviest element being iron. This causes the outer part of the star to expand. As the star expands, its surface cools and becomes a red supergiant. Definitely get those yellows down, guys. The yellows are very important. And then I will move on to the next bit, which is the supernova. They're very interesting. Well, put it this way, a lot of it is just inference, so you don't even know if half of what you're learning is fact. Doesn't a red supergiant expand and cool a few times before it becomes a supernova? Yeah, we're actually going to talk about that now. Oh, no, actually, yeah, you're right. So yeah, the outer part expands, cools, expands and cools. Yeah. Let's go supernova, guys. Okay. You know the structures. I agree. Yeah, you're right, Krish. The structures definitely. So like the red supergiant for sure, but like the sort of the evolutionary stage. I don't know. Surely that is a mathematical inference. Got you. But if it takes millions of years, how have you observed it? Yeah, I agree, Nathan. I know, but like so basically, you're thinking of a lag phase. It doesn't mean that it's sped up. The process is sped up. You're thinking of a lag phase. So yeah, it takes a long time for light to get to us. Wait, so you're saying we can observe stuff in space on like YouTube sped up mode? Bro's got it on like 300x. I don't even think 300x would cut it. Make it make sense, man. Right, let's continue. So we said red supergiant, all the fusion reactions start to run out, the core starts to die down. So the heavier elements are helium to carbon, nitrogen to oxygen, then iron is the last stage. Then there's a series of expanding and cooling until we get to a red supergiant. Let's go on to the supernova. Okay, so once the fusion reactions inside the red supergiant cannot continue, the core of the star will collapse. Suddenly, the outer layers are blown away in a gigantic explosion. This is called a supernova. So once the fusion reactions are supernova, okay, so it will start to collapse, and the outer layers are blown away in a gigantic explosion. So the supernova is the gigantic explosion. At the center of the explosion, a dense body called a neutron star will form. Let's get us down, guys. So collapse suddenly. Okay, then they're blown away in a gigantic explosion called a supernova. So this, yeah. At the center of the explosion, a dense body called a neutron star will form. The outer remnants of the star are ejected, so thrown off, into space during the supernova explosion, forming a new cloud of dust and gas. So pretty much giving birth to the formation of a new star. The nebula from a supernova may form new stars and orbiting planets. That's insane, isn't it? The heaviest elements heavier than iron, are formed during the supernova and are ejected into space. These nebula or nebulae may form in new planetary systems. So they're suggesting that the nebula from from a supernova may form new stars with orbiting planets. So basically, they need mass, don't they? So it's almost like it's absorbing another large mass, and then these make new planetary systems. Sorry, in answer to your question, it doesn't take millions of years. No, but you're witnessing another black hole. You're not witnessing the transition. If that makes sense, dude. How are you following a transition if it takes millions of years? Aren't you seeing another star in another stage? It's like a fossil, right? I see a fossil in one stage, and I assume that fossil turned into this fossil or whatever, like that organism turned into this. Oh, I see what you're saying. Okay. All right, cool. That is very interesting. I did not know that. If it's extremely dense, would that mean that the new star and stuff created could end up orbiting a neutron star? If extremely dense, would that mean that the new stars and the stuff created, as in like absorb into the neutron star? It kind of makes sense, doesn't it? But it depends. It depends how far it's ejected. Imagine it's ejected far out of the gravitational field. Yeah, you're right. Ah, I see what you mean. Well, maybe that's what they mean by planetary systems. I think that's definitely worth a read. Yeah, maybe you're right. I mean, look what it says. It says new stars. So basically, nebula from supernovas will form new stars with orbiting planets. Remember, for a star to form, you need mass. So they're suggesting that that the nebula will literally morph or like sort of and swallow the mass of another orbiting planet. So to form a new star. So yeah. So yeah, guys, just a quick reminder on a supernova. So yeah, once the fusion reactions inside the red supergiant cannot continue, the star collapses. We know that there's a gigantic explosion, okay, called a supernova. Just to clear up a misconception, is the supernova the name of the explosion? Is a supernova the name of the explosion? Yeah, good, good. So the supernova is the name of the explosion, and what's left over is the neutron star, which is super dense. Okay, and then whatever was exploded out into the sort of space, should we say, is going to form the dust and the gas for a new nebula, right? For a new star. Okay, and then sometimes that the nebula will sort of join with orbiting planets and form new stars. Okay. Really? That's crazy. I didn't know that. Chris, I'm hearing some new stuff today, man. That is pretty crazy. So what did you say? What? I know, right? What did you say forms the supernova? Let me go back and read one of your comments. Oh, right. Yeah, sorry, no, I read that right. Yeah, I read that right. No, what you said about the black hole. Okay. Alrighty, guys. Let's continue. Let's continue, guys. Okay, we're going on to the neutron star. The neutron star. Okay. Okay, so neutron star. In the case of the most massive stars, the neutron star that forms at the center will continue to collapse under the force of gravity until it forms a black hole. A black hole is an extremely dense object which has a gravitational pull so strong that not even light can escape from it. Isn't that crazy, guys? That's just so wild. That is so wild. In the case of most massive stars, so then you get a neutron star, right? The neutron star is so dense. So under gravity is collapsing because there's so much pull, and it forms a black hole. A black hole is extremely dense, which has a gravitational pull so strong that not even that's crazy. Let's talk about fusion first. We're going to talk about fusion. It's coming up. Wait, hold on. Maybe we've already covered it. All the naturally occurring elements, apart from hydrogen, have been formed by nuclear fusion. Okay, so basically lower sort of lighter elements joining together to make heavier elements joining together to make even heavier elements, and the list continues. So all the naturally occurring elements, apart from hydrogen, have been formed by nuclear fusion in stars. Nuclear fusion occurs when two light nuclei collide at high speed, joining to create a larger, heavier nucleus. When the universe was formed 13.8 billion years ago, the only element present was hydrogen. If two hydrogen nuclei collide with enough energy, they will fuse into helium nucleus. Okay? Are we good? Are we good on that front? So if two hydrogen nuclei collide with enough energy, they fuse to form helium nucleus. For example, the nuclei of two different isotopes So the nuclei are two different isotopes of hydrogen. So we got protium, which is 1,1, and tritium, which is 3,1, can join to form a helium nucleus by the process of nuclear fusion. Anyone know the name of a hydrogen with two protons? Two neutrons. Yeah, deuterium. Deuterium. Well done. Alpha particle is helium, isn't it? Alpha particle is helium, yeah. How do people know this random stuff? It's some. I think some revision guides. It's in there. I feel like I've seen it before. Yeah, so you got tritium, deuterium, and just protium. Okay. Okay, let's go. So let's continue. So tritium and protium make helium. So two different nuclei collide to make this helium. The process of nuclear fusion releases energy. The energy is released in the form of heat and light. So heat suggesting radiation, light, waves, right? Waves. So a lot of energy is being released. But if you notice, all the particles have been accounted for. Can you see? I actually don't know. I wonder who named it. Okay, but then the mass is accounted for, right? The mass is accounted for, which is what I was trying to allude to earlier, by the way. That's where I was sort of getting at. Right. Let's continue, guys. So, do we all know what sort of these nuclear fusion reactions, the first couple, right? So, sort of like at the beginning of the universe, or the beginning of time, should we say, 13.8 billion years ago, it was only hydrogens available. We had different forms of hydrogens, protium, deuterium, tritium, and that made the heavier elements. Okay, and in the process of fusion, it got a bunch of heat and light. Guys, is there anything you need to note from this page? Let me know. Okay, awesome. The formation of new elements. And we already said that, guys, do you remember when we were looking at the red supergiant? We were looking at the red supergiant. We were saying that the sort of reactions that were taking place were heliums to hydrogen, so regular fusion. Then the heavier elements were forming. There was two other reactions mentioned. One of them was oxygen to nitrogen. Sorry, nitrogen to oxygen. What was the other one? Helium into carbon. Very good. So helium into carbon first, then oxygen into nitrogen second. Sorry, nitrogen to oxygen second, and then iron was right at the end. So iron, yeah, iron is correct. It's the heaviest element. The end product, should we say? And that's when it starts to. What happens after it starts to cool down? What happens to the outer layers? Do you guys remember? Yep, that's right. The supernova. And they sort of both people said kaboom at the same time. Yeah, look, all of that mass is sort of like broken and sort of shot out into the atmosphere. So there's that, and then those go on to make. What does that dust go on to do? What does that explosive sort of that material that has exploded off? What does that go on to do? It goes on to make nebula, very good, which is new stars. With planets can even do that. What's left over in the middle? What's that super dense thing that's left over in the middle? Very good, neutron star. So that's good. I'm glad even after our discussion we were able to recall that. Awesome. Okay, and then obviously after the neutron star you have two. After the supernova, you have two options. You have the neutron star, and then you have the formation of a black hole. And what is a black hole? A black hole is just basically super dense, a lot of gravity pulling in everything, even light. Okay, so let's continue. During the majority of a star, correct, yeah. During the majority of a star's lifetime, hydrogen nuclei fuse together to form helium. So during the majority of a star's lifetime, hydrogen nuclei fuse together to form helium. As a star runs out of energy, other fusion reactions take place, forming forming the nuclei of other elements, for example. And they've given us a couple of examples here, but really we already know about this from before. So they've suggested that two helium nuclei will fuse together, and that forms a beryllium nucleus. So as you can see, the numbers add up. Okay, the beryllium nuclei, they join together and they form carbon. Okay, sorry, a beryllium and a helium will form carbon. So elements lighter than iron are formed in fusion reactions. Elements heavier than iron are produced in supernova explosions. Okay, so elements lighter would probably come from the solar mass star. Okay, and elements heavier than iron most likely come from the red supergiant, and then therefore supernova. So there you go. So we got all of this. Just to remember, I don't think there's anything to note down here, but that's important to know. Right, let's move on, guys. Right, let's go into supernovas. Supernovae. Okay, so a supernova is a bright and powerful explosion that happens at the end of a massive star. A massive star's life. It occurs when the star is bigger than the sun. What's the end product of when a star is not bigger than the sun, or like around the same size? Good, yeah, a black dwarf. So yeah, white dwarf, and then eventually a black dwarf. Yeah. It occurs when the star is bigger than the sun. The explosion releases a large amount of energy. During a supernova, all of the elements which were produced by fusion are expelled along with neutrons. Let's read that one more time. During a supernova, all of the elements which were produced by fusion reactions are expelled along with neutrons. Yeah, just a quick sort of recap. The neutrons combine with the elements to form heavier elements. We already know that. These elements are ejected into the universe by the supernova explosion, and they form new planets and stars. Since the Earth contains many heavy elements, including ones heavier than iron, this is proof that it must have formed from the remnants of one supernova. Okay, and this is so interesting, guys, because iron essentially has come from outer space. Okay, this is so interesting. Iron has actually come from outer space. Okay, very sort of profound thing here, because of course that's like impossible to know, right? Impossible to do. It's only science that could have caused us to get to that point, to get to that understanding of knowing where it's come from. And let me just show you this. By the way, guys, this is the reason why I'm a theist, man, because my religion talks about this stuff, and when I've read about it, I was like, wow, that's pretty crazy. But I don't want to get preachy, but that's just want to tell you why I sort of have certain views on certain things. What's the word I'm looking for? I like to what's the word? A theist is someone who believes in a religion. Atheist is someone who's without religion. But yeah, because like I was researching this, I was thinking, what? Like iron coming from outer space, and my like religious book talks about that. So for me, that's a sign that this is making sense. This is 100% making sense. But yeah, yeah, 100% Krish. But to be honest with you, like when I'm thinking about like even the stuff that we're talking about today, it just goes against your fundamental understanding of maths, doesn't it? 100% Ardian, exactly. No, like just like I mean, just like the concept of no. Like, you know when you what you've learned as in basic physics, you've learned that you have the conservation of mass in chemistry. You have the conservation of energy, don't you? The conservation of energy in physics. And what are these principles? Nothing can be created nor destroyed. So it's almost like it's a cycle, an infinite cycle. So that means that mass that is there will always be there. It can never just sort of disappear. It can only be sort of be relocated. No, no, no. I know that, Krish. So what I'm saying is that will then definitely go against what we know about like fundamental maths, like just basic stuff, if that makes sense. Like you have to kind of be willing to go against your sort of core mathematical beliefs, basically, to accept those phenomena. That's what I meant. Okay, cool. Yo, you know what? I'm gonna admit that I probably have some reading to do on that front, so I'll look into it. Orbital motion. Let's talk about centripetal force, and this is really weird, by the way. So let's introduce it now, and then we'll go into it next lesson. Okay, so orbital motion. Orbital motion. Let's get into it. So yeah, so they eat matter and white holes spit it out on the other side. Therefore, mass doesn't get destroyed. Well, if that is the case, then I guess that explains a lot, doesn't it? Explains the mass conundrum. But you know what? Ask your physics teacher. See what they say. Right, there are many orbiting objects in our solar system. They each orbit a different type of planetary body. So here you have a planetary body or celestial body, planet, moon, comet, asteroid. Ooh, quick one, guys. What's the difference between a comet, an asteroid, and a meteor? Let's see if you remember the difference. A comet, an asteroid, and a meteor. Sorry, just a bit of a side point. A comet orbits the sun in a way different to an asteroid. Comet is made of ice, that's true. A meteor enters the atmosphere. What does it look like? What does a meteor look like when it enters the atmosphere and turns into gas? It looks like a streak of what? A streak of light. And an okay, good. And let's just see what you guys said about asteroid. Fantastic. So it's like rocky, good, orbits the sun. Usually in a belt, right? Where's the belt? Between what two planets is the belt? The asteroid belt. There's rocky planets and there's what? What's the other planets? Gaseous planets, right? What's the boundary? So between the last rocky planet is Mars, and the first gaseous planet is Jupiter. So it's between Mars and Jupiter. You guys remember that, right? A smaller body or object will orbit a larger body. In order to orbit a body such as a star or a planet, there has to be a force pulling them in. So of course, gravity. The gravitational force exerted by a larger body on the object is always attractive. Therefore, gravitational force is always acts towards the center of the larger body. The gravitational force is the centripetal force, as it will cause the body to move and maintain a circular path. So it's almost like a pulling in motion. Yeah, everyone been on one of those spinning things in the park. You know those things you have to run and sort of like when you hang your head out, you like feel so weird and you pull it in. Okay, so that's centripetal force. We're going to talk about centripetal force next lesson. I'm going to go into like a lot of detail with it. But just very quickly, just want to show you the sort of path that we're talking about. Okay, so here you have it. You have a large mass at the center, okay, the Earth, and then you got a moon, which is a natural satellite being sort of pulled around the Earth in a circular motion. Okay, why is it that the moon orbits the Earth? It's because of the mass. Guys, why doesn't the moon orbit the sun? If the sun is a larger mass than the moon. Yeah, very good. Basically, it's all about distance. So you got to be in the proximity, or you got to be in the field. You got to be in the field. So the moon is in the field, the gravitational field of the Earth, purely due to distance, whereas the Earth is in the field of the sun, again due to distance. So the moon is, because it's closer to the Earth, it's going to orbit the Earth as opposed to orbiting the sun. Guys, quick one. What's the purpose? What purposes of the moon can you think of? Side point. One purpose of the moon that you can think of. Reflected light. Fair enough. By waves, do you mean tidal waves? Yeah. That's one thing that we sort of learn. And another one is like something to do with the tilt of the Earth. You know, the axes.